Hello, everyone, and welcome to this lecture on predicting house prices using a regression example. In this session, we will cover a few key topics. First, we'll introduce the Boston housing price dataset. Then, we'll discuss preparing the data for our model. Next, we'll build our neural network. Finally, we'll explore validating our approach using a technique called K-fold validation. Let's start with the Boston housing price dataset. This is a classic dataset in machine learning, commonly used for regression tasks. It contains information about houses in the Boston area and their median value. The dataset includes 13 features such as crime rate, number of rooms, and distance to employment centers. And our target variable is the median value of owner-occupied homes measured in thousands of dollars. We can load the dataset using TensorFlow's Keras datasets module like this. As you can see from the output, we have separate training and test sets for both the data and the target values. Now, let's move on to preparing the data. The features in the Boston housing dataset have different scales. For instance, the crime rate is a small value, while the number of rooms is a larger number. Neural networks generally perform better when the input features are scaled to a similar range. A common and effective technique for this is feature-wise normalization. This involves subtracting the mean of each feature and then dividing by its standard deviation. The formula for normalization is x normalized equals x minus the mean divided by the standard deviation. Here, x is the original feature value, mu represents the mean, and sigma represents the standard deviation. We can implement this normalization using numpy, like so. Notice how the values are now centered around 0 and have a similar scale. Next, we will build our neural network. For this regression task, we will use a simple feed-forward neural network. Our network will consist of two hidden layers, both using the rectified linear unit, or ReLU, activation function, and an output layer with no activation, which is typical for regression problems. Since we are predicting a single continuous value, the house price, the output layer will have just one unit. For regression, the standard loss function is mean squared error, or MSE. The formula for MSE is the sum of the squared differences between the actual target value, yi, and the predicted target value, y hat I, divided by the number of samples n. We will use the atom optimizer to train our model. We'll also monitor the mean absolute error, or MAE, during training, as it's often easier to interpret than MSE. The formula for MAE is the sum of the absolute differences between yi and y hat I divided by n. Here is the Python function to build our model. The model summary shows the layers and the number of parameters. Now, let's discuss validating our approach using K-fold validation. Since the dataset is relatively small, a simple train validation test split might result in a validation set that's too small to be truly representative of the data. K-fold cross-validation helps address this. In this technique, we split the data into K-folds. For each fold, we train the model on the data from the other K-1 folds and then evaluate it on the held-out fold. We repeat this process for each fold and then average the evaluation metrics to get a more reliable estimate of the model's performance. This provides a more robust assessment than a single train validation split. We can implement K-fold cross-validation in code as follows. The output shows the average MAE across all folds, giving us a good indication of the model's expected performance. We can also visualize the validation result by plotting the average MAE for each training epoch across all folds. We can see how the model's performance evolves during training and identify potential issues like overfitting. The plot helps us determine the optimal number of epochs to train our model. Finally, we perform the final training. After determining the optimal number of epochs from our validation results, we train the final model on the entire training dataset for that specific number of epochs. Then we evaluate this final model on the unseen test data to get a final estimate of its performance on new, previously unseen data. We rebuild a fresh model and train it on the entire training data. The test MAE score provides an indication of the model's average prediction error on unseen data in thousands of dollars. In summary, in conclusion, this notebook demonstrated how to build and evaluate a neural network for predicting house prices using the Boston housing dataset. We learned the importance of normalizing the data to improve model performance. We built a sequential model using dense layers. We utilized k-fold cross-validation as a robust validation technique, especially valuable for smaller data sets to understand the model's performance during training. Finally, we trained the final model on the full training data and evaluated it on the test set. The final mean absolute error on the test set gives us an indication of how well our model is likely to perform in predicting house prices on new data. This notebook illustrates a fundamental approach to solving regression problems with neural networks and emphasizes the significance of data preparation and robust validation. This concludes our lecture note on predicting house prices. Thank you for your attention.